Bismillahirrahmanirrahim. Lecture number 11A, Ideal Heat Engine and Refrigeration. In the last lecture, we did the Carnot cycle and we were able to define the or find the efficiency of the Carnot cycle. And we were saying like it's the maximum efficiency of any engine that worked between the two temperature reservoirs. So in finding the efficiency, which was equal to efficiency was equal to 1 minus TL by TH, or that was 1 minus QL by QH. So in either case, like the efficiency would be only 100% if QR or the Q rejected is equal, or the Q lower is equal to 0, or the temperature, which is actually TL, is absolute 0. Or either if you can imagine like the temperature TH is up the infinity temperature, then in that case the thermal efficiency of the Carnot cycle would be 100%. Let's have a generalized representation of any thermodynamics heat engine. The thermodynamic heat engine work between two temperature reservoirs. One is high temperature reservoir and one is actually the low temperature reservoir. The high temperature reservoir would be, we would be extracting heat from the high temperature reservoir, uh, QH, and we would be doing some work done, and which is W over here, and heat would be rejected into a low temperature reservoir. This is the generalized thermodynamic cycle. That's what we're saying, like working between the two temperature reservoir. And by doing so, the entropy of the system would be changing, and that would be entropy would be increasing. Let's move forward to the Carnot cycle. And in Carnot cycle, we like in the last lecture we did say like the Carnot cycle worked between the two temperature reservoir, and we were assuming like those temperature reservoir were not changing its temperature. In other words, when we were extracting heat from the high temperature reservoir, the temperature of the high temperature reservoir was not changing, and when we were rejecting the heat into the low temperature reservoir, the temperature of the low temperature reservoir were not increasing. Another way, what we are saying like the in during the heat absorption and heat rejection, the temperature of the reservoir remain constant. So let's start with the Carnot cycle, and let's assume like, or let's have a PV diagram of a Carnot cycle. So let me draw a PV diagram in here, and let me draw two temperature lines. Let me say like a two temperature isothermal lines, and let me say like one we have got the temperature TH over here, and the other one we have got the temperature TL. But what we are saying like the temperature throughout on this line remain constant, and the temperature throughout on this line TL remain constant. So these are our two isothermal temperature lines. Let us start the Carnot cycle, or let us construct a Carnot cycle using the concept which we are familiar with. Uh, Let me say like, let's say in a first figure, if I'm saying like I've got a piston and cylinder arrangement, and my piston is actually at the top dead center. The top dead center is where we are having the uh, mm, exhaust and inlet valves, or in which, if I'm saying like when the volume of the swap volume is equal to the minimum, then we are saying like we are at the top dead center. So let it be like we are the top dead center, and the piston is at the minimum volume. So let me say like we have got the minimum volume somewhere at the point A, somewhere here. So this is actually what we call it as a, this volume we will call it as a clearance volume. Like there is a little bit volume still there, but we will call it normally clearance volume. So we are having a piston and cylinder arrangement which is at the top dead center. Let me put this piston and cylinder arrangement on a high temperature reservoir, which is actually at TH. So what would normally happen? The this piston arrangement will try to absorb heat from the high temperature reservoir, absorb heat, let's say high temperature heat from the high temperature reservoir. And when it is actually absorbing heat, the pressure will try to increase in order to keep the pressure constant, or in order to keep the pressure balance. The piston will start moving upward. So in other term, what we are having is during the heat absorption, there will be expansion of the piston. And we have already said, like in our conceptual Carnot cycle, that the temperature of the system should remain constant. So that means, like, when you are supplying heat, the temperature would remain constant, there would be heat absorption, and there would be expansion in a piston and cylinder arrangement. So that means, like, we are going from the state A to state B, somewhere here. Let me change the color of this one. So we are having moving from state A to state B, and that's what we call it as an isothermal expansion. And that isothermal thermal expansion, what we are saying, like, we are absorbing heat, which is absorbing heat at QH. Now what, let's say, like, we actually remove this reservoir, and when we are removing this reservoir, let me thermally lag it as well, so there is no heat losses from the piston and cylinder arrangement. So what would happen, like, as there is heat inside the cylinder, so what would happen, the piston would still rise even though we are not supplying heat to the system, and the piston will rise up to the end, which is the bottom dead center. So what I mean to say, like, that there is no heat supply to the system is not taking any heat from the outside, but still the piston is actually expanding. So for the first law of thermodynamics, if you can imagine, the change in internal energy is equal to the heat supplied minus work done. That was actually our first law of thermodynamics. So in that case, if I'm saying, like, the there is no change in, there is no heat supplied, so that means, like, there is no heat supplied over here, and we are just saying, like, there would be work done, there would be expansion, but that expansion would be at the expense of change in internal energy. And that mean, like, if there in expansion mean, like, we are having a positive work done, so that mean the change in internal energy would be negative. Change in internal energy negative would mean the temperature would be decreasing. So what we are saying, like, we are moving from A to B. That was isothermal process when we are supplying heat from the high temperature reservoir. But when we stop supplying heat to the system, there is still an expansion, and that expansion is from B to C. But that expansion is reversible adiabatic expansion, and that expansion, in that expansion, the internal energy is decreasing while there is some work done from the system on the surrounding. So now we have reached the bottom dead center, where we have got the maximum volume. Remember, we have got the minimum volume at the top dead center, and we have got the maximum volume at the bottom dead center. So we have reached the bottom dead center over here. We have got the maximum volume at the bottom dead center somewhere here, and we are at temperature, which is at the reservoir at temperature, which we have got TL. Or let me say, like, when we put TL over here, now when we are at the bottom dead center, we just put the temperature reservoir TL over here. So when we put TL, when we put the, or in other word, when we put the system on the temperature reservoir TL, so the heat which is actually inside the system, it will move from the system to the temperature reservoir at TL. So the heat is flowing from the system into the surrounding, or in other word, into the low temperature reservoir. So what would happen, like, the volume would try to decrease, it would try to squeeze together. So when they are squeezing together, the volume would be decreasing, and when the volume is decreasing, actually what we call it as compression. So that in what we are saying, like when we are putting the system on a low temperature reservoir, there is actually a heat loss from the system, and there is actually a compression. Again, assuming like we are talking about the Carnot cycle, and we are talking about the process in which the heat is lost during the isothermal process. So what I'm saying, like from C to D, there is an compression, there is heat loss from the system, and it is actually, we call it as isothermal compression. Now again, removing the reservoir. So from C to D, we have got heat removal from the system to a low temperature reservoir. Now again, we take the low temperature reservoir out, or we just remove the low temperature reservoir and let the piston still compress from D onward. So what would happen, like there would be still piston moving, and that would be moving towards the top dead center, and we have removed the temperature reservoir. In other words, what we have already said like earlier, so we would be having work done, and that would be work done by the surrounding on a system. In other words, we have got the compression work done. That means like we would be having a negative work done. In negative work done, we would be having increase in internal energy. So increase in internal energy mean like we would be having an increase in the temperature. So when we are having an increase in temperature, and there is actually a compression process. So and that compression process was when we have removed the heat, and that mean like we are moving in an adiabatic process. So that mean like from D to A, we would be having an adiabatic, reversible adiabatic compression. So let me rewind it again. So and let me move to the next figure, are properly figured so that you would understand. So we are having four processes now. Process from A to B, which was when we are having the temperature constant and there was heat absorption in a system. We are having a process from B to C when we have removed the reservoir. That means like we are not supplying heat into and out of the system. So the process was adiabatic process. The process from C to D, when we have put the system on a low temperature reservoir and we are rejecting heat from the system to the surrounding, and the process was isothermal process. And then we are moving from D to A when we have removed that even the low temperature reservoir, and we have allowed the piston to move towards the top dead center, and the process was the adiabatic process. So we have got four processes: two isothermal process and two adiabatic process. From A to B, we have got the isothermal expansion in which the heat is absorbed. From C to D, we have got isothermal compression in which the heat is rejected. From B to C, we have got adiabatic expansion in which the temperature is dropped from temperature T high towards the T low. And from D to A, we have got the isothermal compression in which the temperature is increased from TL to TH. So this is all the four processes of the Carnot cycle. Carnot, from A to B, isothermal expansion; D to C, adiabatic expansion; from C to D, isothermal compression; from D to A, adiabatic compression. So the system is kept. So that means like the thermal efficiency of the cycle, which is equal to 1 minus T 1 minus TL by TH, which we have derived in a previous lecture, or 1 minus q rejected by q accepted. If you are familiar with 1 minus ql, which is q lost, by qh, which is actually high temperature reservoir heat which is absorbed. Now, looking at the individual legs or individual processes, so there was actually a process from A to B, which was the isothermal process. So in isothermal process, as we have done a little bit earlier over here, for the first law of thermodynamics. So isothermal process is change in internal energy is equal to heat supply minus work done. So during the isothermal, is there is no temperature changes, so that means like change in internal energy would be equal to zero, and whatever the heat supply would be equal to the work done. So that means like when we are supplying heat to the from A to B, heat supplied, which is QH from A to B, that is actually equal to PV is equal to RT. If you remember, PV is equal to RT log of V2 by V1. So that means like log of V2, V, which is actually VB, by V1, which is actually VA over here. So this is the heat transfer in an isothermal process, which is actually from A to B. Similarly, the heat transfer in an isothermal process from C to D would be equal to somewhere here, as it is actually in a opposite direction. So make sure like that would be actually in a negative sign over here. What I mean, like the opposite direction, from A to B we have got the expansion, from C to D we have got the compression. Putting the value, and we would be having this kind of an equation, although we are yet not there to define or to derive the thermal efficiency, simple equation of the thermal efficiency of the Carnot cycle, but this is the equation of the thermal efficiency so far for the Carnot cycle. Now we do have like other legs or other processes in the Carnot cycle as well. Carnot, the process from B to C, which is adiabatic expansion, and from D to A, which is adiabatic compression. So remember from the previous notes, if you imagine, we have said like at the adiabatic process, we define an adiabatic process which is equal to TB, gamma minus 1 is equal to constant. And that's what actually you have solved in your midterm exam as well. So that means like for the adiabatic process, T2, which was equal to TH, VB gamma minus 1 is equal to TL, VC gamma minus 1. Putting them in here, so we would be having an equation which would something look like this. Putting that equation in here, we would be able to find the equation which would be equal to efficiency of the Carnot cycle. I hope like you could solve that equation. If there is any problem, please let me know in your classroom. So this is the thermal efficiency of the Carnot cycle. We have derived the thermal efficiency of the Carnot cycle in a previous example, in a previous lecture differently, but now we have derived the thermal efficiency of the Carnot cycle differently now. In exam, like whatever method you would understand, you can derive, or whatever method is actually required, you can solve using that method.